Our planet is facing a significant challenge. The climate is changing and human activities are the primary cause. We burn fossil fuels like coal, oil and gas to power our homes, industries and transport. This process releases vast quantities of carbon dioxide, or CO2, into the atmosphere. This gas acts like a blanket, trapping heat and causing the Earth's temperature to rise. This phenomenon is known as global warming, and its effects are becoming more apparent every day. We see more extreme weather events, rising sea levels, and disruptions to delicate ecosystems across the globe. The scientific community agrees that we must act now to reduce these emissions. To address this climate crisis, the world is turning to a range of solutions. Renewable energy sources, such as solar and wind power, are becoming more common. Improving energy efficiency is another vital step, meaning we use less energy to achieve the same results. However, transitioning our entire global energy system will take time. Many essential industries like cement and steel production are particularly difficult to decarbonize. These sectors are fundamental to our modern society, but their processes inherently release large amounts of CO2. This is where a technology known as carbon capture and storage, or CCS, enters the conversation. It is presented as a potential bridge, a tool that could help us manage emissions while we continue to develop and implement long-term sustainable solutions. The idea behind CCS is straightforward in principle. Instead of allowing CO2 to escape into the atmosphere, we capture it from large industrial sources. Once captured, this CO2 is transported and then permanently stored, usually deep underground. The urgency of our climate goals has pushed CCS into the spotlight. International agreements, such as the Paris Agreement, aim to limit global warming to well below 2 degrees Celsius. The International Energy Agency and other major organizations have stated that CCS could play a crucial role in achieving net zero emissions. It's not seen as a replacement for renewable energy or energy efficiency, but rather as a complementary technology. So what is this technology in more detail? Carbon capture and storage is a three-step process. The first step is capture. This involves separating the carbon dioxide from other gases produced by industrial processes or power generation. The second step is transport. Once the CO2 has been captured and purified, it needs to be moved to a suitable storage location. The most common way to transport large volumes of CO2 is through pipelines. The third and final step is storage. The captured CO2 is injected deep into the Earth's crust for permanent storage. These formations are located thousands of feet beneath the surface and are capped by a layer of impermeable rock, which acts as a natural seal. In essence, CCS technology takes a waste product from our industrial age and puts it back where it came from. The concept of capturing carbon dioxide is not as recent as one might think. Its origins can be traced back several decades, long before climate change became a prominent global concern. For instance, in the 1920s, processes were created to remove carbon dioxide from natural gas streams. This was done because CO2 is a corrosive impurity. Since the 1970s, oil companies have been injecting CO2 into aging oil fields in a process called enhanced oil recovery, or EOR. The first large-scale project that combined capture with dedicated injection for EOR began in 1972 in Val Verde, Texas. The transition of carbon capture to a climate mitigation strategy began in the late 1980s and early 1990s, as the scientific consensus on man-made climate change was growing stronger. A landmark moment came in 1996 with the launch of the Sleipner project in Norway. This was the world's first dedicated large-scale CCS project designed specifically for climate reasons. The captured CO2 was injected into a deep saline aquifer. It demonstrated that storing large volumes of CO2 was not only possible, but also safe and effective. Following Sleipner's success, interest in CCS grew steadily, transforming it from a historical industrial practice into a modern and debated climate solution. One of the main methods for capturing carbon dioxide is known as pre-combustion capture. This involves removing the carbon from the fuel source before it is even burned. The syngas undergoes a second stage called the water-gas shift reaction, which transforms it into a new gas stream that is now highly concentrated in both hydrogen and CO2. The CO2 is then separated, leaving behind a stream of almost pure hydrogen. The hydrogen, now a carbon-free fuel, can be used to generate electricity, producing only water when burned. However, its main drawback is that it is a complex and capital-intensive option best suited for newly built industrial plants. The most widely known method is post-combustion capture. This technology is designed to remove carbon dioxide after the fuel has already been burned. Within this capture unit, the flue gas is passed through a liquid chemical solvent. The solvent selectively binds with the CO2 molecules, much like a sponge soaking up water. The CO2-rich solvent is then heated. This reverses the chemical reaction, causing the solvent to release the captured carbon dioxide in a highly concentrated, almost pure form. The process creates an energy penalty, reducing the overall net power output of the plant. A third major method is called oxycombustion. This approach takes a different route by changing the conditions under which the fuel is burned. This oxygen, instead of normal air, is then used to burn the fossil fuel. Burning fuel in pure oxygen results in a flue gas that consists almost entirely of just carbon dioxide and water vapor. The resulting flue gas is cooled. The water vapor condenses and can be easily removed, leaving behind a stream of very high purity carbon dioxide. However, the main challenge and cost lie in the air separation unit, which is a large, complex and energy-intensive piece of equipment. Once carbon dioxide has been successfully captured, the next crucial step is to transport it. The most mature and cost-effective method is through a network of pipelines. The captured CO2 gas is first compressed into a dense, liquid-like state known as a supercritical fluid. Safety is a paramount concern. Pipelines are built to stringent engineering standards with continuous monitoring to prevent leaks. While pipelines are preferred for large volumes, shipping is emerging as a particularly flexible alternative, especially for crossing large bodies of water. For even smaller quantities or for transport over shorter distances, road and rail tankers can also be used. Ultimately, a fully developed CCS system will likely rely on a combination of all these transport methods, creating an integrated and resilient network. The final and most critical stage is permanent storage. This involves injecting the CO2 deep into the Earth's crust, typically more than 1 kilometer beneath the surface. The most common locations are depleted oil and gas reservoirs. Another highly promising option is deep saline aquifers. A third option is to inject CO2 into deep, unminable coal seams. A potential site must have a layer of porous rock to hold the CO2, and most importantly, this reservoir must be sealed from above by an extensive layer of impermeable rock, known as the cap rock. Once injection starts, a comprehensive monitoring program is put in place. This is essential to track the behavior of the injected carbon dioxide and ensure it is staying securely within the intended formation. The security of geological storage relies on a combination of physical and chemical trapping processes that become stronger over time. From structural trapping by the cap rock to residual and solubility trapping, and finally over thousands of years mineral trapping where the CO2 is turned back into solid rock. One of the most significant benefits of carbon capture is its ability to tackle emissions from sectors that are notoriously difficult to decarbonize. Furthermore, carbon capture can be applied to the production of blue hydrogen, allowing for the large-scale production of low-carbon hydrogen today. Another key benefit is that CCS is one of the few technologies capable of delivering negative emissions when combined with bioenergy, a process known as BECCS. Despite its potential benefits, carbon capture and storage faces significant criticism, with its high cost being the most prominent drawback. Beyond the economic challenges, there are public and environmental concerns regarding the long-term safety of carbon dioxide storage, including the potential for leakage or induced seismicity. Another major argument is the concern that it represents a moral hazard that could prolong our dependence on fossil fuels, diverting investment away from renewable energy. In our journey, we've seen that CCS is a technology of great complexity and significant potential, yet one that is also fraught with challenges and controversy. The immense costs mean that its deployment is entirely dependent on robust and sustained policy support from governments, such as a meaningful price on carbon. Ultimately, carbon capture and storage is best understood as one piece of a much larger puzzle. It is not a silver bullet nor a substitute for the rapid expansion of clean energy. Its true value may lie in its application as a targeted solution for the hardest to abate sectors. The future of CCS will depend on continued innovation, strong political will, and a clear-eyed public conversation about its proper place within a diverse portfolio of climate solutions needed to protect our planet.